Hello, what is up everyone, and welcome back to a very different kind of video. I know some of my friends in Calc BC got integration by parts coming up, and just figured I wanted to do a video on some problems about it, because I figured that would be fun. So I'm going to show two kind of examples of harder, more interesting integration by parts problems in this video. I'll write down the first one now. So we're going to be looking at the integral of arc sine of cosine of x, which I thought was interesting. So the approach really for this problem is similar to if you've done like ln x. This is one of the few places where I think you have to have some like creativity with integration by parts, which is where you realize that you can write, like I did there, any function f of x as f of x times 1. And then integrate by parts that way, where of course you're going to integrate 1 and derive your f of x. And so here what we're going to get is x arc sine cosine of x just from integrating 1. And then be careful with this integral that you're subtracting, because you have to take the derivative of the arc sine. So that's going to be 1 over root 1 minus x squared, which I'm getting to. I'm doing this as like a voiceover because I didn't want to have to hear the mouse clicking as I'm drawing all this out. And the x is there also because that's our g function. That's the one that we integrated. And then, of course, on the bottom, since it's arcsine of cosine of x, the cosine, you stick that in for x, so that'll be square on the bottom. And then, of course, don't forget the chain rule, so you multiply by negative sine x, since that's the derivative of cosine x, and then go ahead and close that. And of course you got two negatives, so you can go and make that positive. Now this looks really nasty, although there's a really good identity you can use here to actually simplify this way down, which is that if you look at the Pythagorean identity, you can see from that 1 minus cosine squared x is actually just going to be equal to sine squared x, and that's under a square root, so that'll just become sine x. And then as you can see, this will actually simplify quite well, because the sine x that you had on top from the chain rule will just go away with the sine x on the bottom. I'm also sorry for the handwriting being kind of messy. I'm doing this in MS Paint, so it's a little bit rough. Alright, so now we can go ahead and write down. So again, that just simplifies to x, so we just have the integral of x, so that's obviously quite easy. So our final answer is just going to be x arc sine cosine of x plus x squared over 2, because that's the antiderivative of just x. And then go ahead and put down your plus c, and you're done. So that was the first problem, definitely the easier one of the two. And now we'll go ahead and move on to the second one. So for our second problem, we're going to be integrating e to the power of arc cosine of x. So this is an interesting problem, because you can't integrate by parts right away. We're actually going to have to do a substitution, and we're going to let u be equal to arc cosine of x. And so we're just doing, once we do a substitution, it'll be in a form that we can integrate by parts. And there'll be something interesting that happens when we integrate by parts, which is why I included this problem. So for your du, it's the same derivative as the arc cosine, but just negative, so negative 1 over root 1 minus x squared dx. And then to get to the dx, you just divide du by your derivative there, and that 1 will go away, so it'll just be negative root 1 minus x squared du. But something to notice here is that if u is arc cosine of x, that'll actually mean that, to find what x is, if you do cosine on both sides, it'll cosine of arc cosine, so those will cancel each other out because they're inverses. So you'll find that x is actually just equal to cosine of u. So I'm just showing that. Cosine of arc cosine goes away, so you just have the x cosine u. So that means that the dx will actually just be equal to negative sine u, because if you use the same identity from before, you'll get sine squared in the square root. So you'll just get negative sine of u du as your dx. So now we can go ahead and rewrite our integral. I'm going to pull the negative out front, and I'm actually not going to multiply by the negative until the very end, just because I don't want it to get confusing when we integrate this because it gets kind of nasty. So we have e to the u sine u du, and as that's a product of two functions, this is of course going to be integration by parts now that we've done the substitution. So you can integrate either one. I just choose integrate e to the u since I find that to be a little easier. At least I know the derivatives of the trig functions better than the integrals. So again, like I said, I'm going to integrate it as if it was positive first and then just throw on the negative at the very end because I don't want to get confused because there will be a lot of negatives. So you're going to get e to the u and then just sine u because you keep the sine u the same because that's what we're going to differentiate in the second integral. And of course, integral of e to the u is just still e to the u. Then subtraction, or then you're going to subtract your second integral. And so now you're going to derive sine u, which will be positive cosine u. Once I write that down. And again, you can do this either way. I'm just integrating e to the u because I find that to be a little bit easier. So you go ahead and close that. And as you can see, there's a bit of an issue here because that integral also requires integration by parts. So we're going to have to do it again. So you still have e to the u sine u. That's the first part of the answer. And then subtract. And I'm going to put a parentheses here because, of course, when you integrate by parts, you get two separate expressions. So we need to make sure that we distribute that negative sign so that we don't make a mistake there. So I'm just going to put the whole thing in parentheses first and then distribute the negative at the end. And so inside the parentheses, first thing we're going to get is, again, just going to be like the first one will be e to the u cosine u since it's cosine this time. And then, of course, you subtract and then your integral. And now when you derive cosine, you get negative sine. So you're going to get negative and then e to the u sine u du. So here's again where you need to be really careful because there's like 3 negatives in here and you need to distribute the one from the beginning. So you're going to get e to the u sine u. And then you'll still just have minus e to the u cosine u. And then you have plus, plus, and negative, so that'll become a negative of that integral. That's e to the u sine u du. And so now here's where you need to notice something that is interesting and why I picked this problem again. You'll see that the thing that we were solving for in the beginning is e to the u sine u. And that's actually exactly what we have on the other side. So we can actually just add it to both sides. So we'll get 2 times our integral that we want is equal to the e to the u sine u minus e to the u cosine u. This is kind of the reason I picked problems like these was the first problem because it had the times 1 and the second problem because this has this phenomenon where you get phenomenon. That's a nerdy word. This occurrence where you get the same integral, and so you have to divide by 2. Because most of the integration by parts, if it's a problem where it's just like x cosine x or something, right? There's no like ingenuity there. It's just you see what to do immediately. This takes some thought, and so I'm just multiplying by -1 here because I took that out in the beginning. So you can just flip the order, so this be e to the u cosine u minus e to the u sine u instead of the other way around. All right, so I need to clear up some space, and we'll go and write it down again. So we've got e to the u cosine u minus e to the u sine u, and that'll be over 2. And so we do have the integral evaluated now, and we just have we have one last step, which is, of course, you need to plug whatever u was back into u. Although there'll be a slight issue there. Cosine of u is not bad because that's cosine of arc cosine, so those are inverse, so you just get x. But how do you express sine of arc cosine of x? Like, what does that equal? And so the way we're actually going to do this is I'm just going to let arc cosine x be equal to some angle theta, because remember that even though arc cosine of x is some function, it gives you some output, and that's still just an angle that you're doing sine of. And so we're going to use that Pythagorean identity again here, because we know that sine of theta is just equal to square root of 1 minus cosine squared theta, as that'll just give you sine squared theta in there, and then you take the square root. But this helps us here because we know that cosine of theta is cosine of arc cosine of x, which is just x. So therefore we can conclude that sine of arc cosine of x is actually equal to the square root of 1 minus x squared. And now finally we're about done. We can go ahead and plug arc cosine x back into u. So I have e to the arc cosine x times x, because cosine of arc cosine of x is just x, then minus e to the arc cosine x times sine of arc cosine of x, which is root 1 minus x squared. And that's still all over 2. That was a really bad 2. It looks like a 3. And then finally, we can simplify it by pulling out the arc cosine of x, or the e to the arc cosine of x, and distribute that, and it'll be times x minus square root of 1 minus x squared. And then it'll be over 2. And then just putting your plus c. So, it was a bad plus sign too. I hope you guys enjoyed that. Just a short little fun video, just for fun, and some people were kind of requesting it, so hope you enjoyed. Hope it helps you guys out. I'll see y'all later.